Hey guys, welcome back. This is our last topic for Chapter 4, and this one's going to be over throttling devices. A throttling device, basically what that's going to allow us to do is it will give us a reduction in pressure by introducing a restriction into the line where fluid flows. So example, if let's say you had a water hose out in the backyard and you took a sponge and put that sponge in front of the opening of the water hose and turned the water on, that's going to kind of slow down the flow of that water, right? So that's kind of what we're talking about here. So we could have porous media. You could have a valve that can open and close, so you could partially open that valve to change your flow. So it's things like that. That's what we're going to be talking about with a throttling device. And let's look at our equation. This is going to be another application of that energy balance equation. We're going to assume steady state. So 0 will be on that left side. That will equal QCV dot minus W dot plus M dot times H1 minus H2 plus V1 squared minus V2 squared over 2 plus G times Z1 minus Z2. And typically we're going to ignore the kinetic and the potential effects. Don't always have to, but usually we do. And in this case, we aren't going to need any sort of external power or work. So this is going to go away, and we're not really going to have any external heat transfer unless it's stated. So usually this can go away also. All right, so we'll put this and we'll put unless stated. Sometimes you'll have it, but sometimes not. And these two, you can mark through those. So unless it's stated, you can kind of just get rid of those. That's going to leave us, if all of these things are canceled out, with 0 equals m dot times h1 minus h2. Now, if you look at this, since 0 is on the left side, you could divide both of these sides by m dot, and that just leaves you with the fact that h1 has to equal h2, and the way it works out is your pressure at P2 would be less than your initial pressure. So you're going to reduce that pressure by introducing this restriction into your flow. All right. So let's go ahead and do an example of this, and we'll kind of see how it works. We're going to have ammonia enter the expansion valve of a refrigeration system at a pressure of 10 bar and a temperature of 24 degrees Celsius. It exits at a pressure of 1 bar. We want to know what is the quality of the refrigerant that's exiting the valve. Remember, quality is X. Right? So that's what we will have. Now, we have an expansion valve, so anytime you see a valve, that indicates some kind of throttling device. Let's write our equation down. Here we weren't told anything about a Q dot, so we can assume that's gone. W dot, nothing there. No velocities, no kinetic energy, and no potential, so those are all gone. That's going to leave us with 0 equals m dot times h1 minus h2. So we know h1 equals h2. Now we need to find our values. Okay, so we started out with a pressure of 10 bar and a temperature of 24. Actually, I'm going to draw a box here to represent the system here. Our input, just so it's easier to see, there's our pressure, 10 bar, and our temperature is 24. When we exit, we are at a pressure of 1 bar, and we want the quality. Now at 10 bar, let's see what we have. what we want to do here is let's look at our saturated ammonia table. Let's look at this pressure, 10 bar. And this is table A14 in the Moran book. So 10 bar was our pressure. Here it is. Saturation temperature is 24.89. I'm going to go ahead and draw this on here because I want to show you what happens with this as we go through here. Alright, so this is our 10 bar line. This temperature here is 24.89. Our temperature, it says, is just 24. Now, that's pretty close. So 24, I mean, is really right underneath here. So technically, we're down in here. So technically, we have a compressed liquid. But remember, we said that we could approximate that compressed liquid with the HF value, that saturated liquid point. So that's what we're going to do here, because this is close enough that we can make that approximation. Let's write all this down. So at 10 bar, we've got a saturated liquid ammonia at a temperature of 24.89. All right, so that's your saturation temperature. And at 24 degrees Celsius, which is what it tells us we have, we can say that H1 is approximately equal to HF, just because we talked about that approximation method of using saturated liquid to approximate a compressed liquid. Now in the table, if you go to the pressure 10 bar and look up HF, here's 10, come over here to HF, it's right here, you get 297.76. So there's 297.76 units are kilojoules per kilogram. Now we already said from up here that H1 has to equal H2. So that means that our H2 is approximately equal to 297.76 kilojoules per kilogram. Now we found both of our values, one table. All right. So now we have that. We're looking for quality. We don't have an equation for quality yet, right? But we can find one. We've got these enthalpy values. Remember, we have the relationship that says H equals HF plus X, which is quality, times Hg minus HF. This means we can use this equation to solve for quality. We're going to do that at the exit point. So we'll use a 2 subscript to represent the exit. If we solve this equation for x, we can put x2 equals H2 minus HF2 divided by Hg2 minus HF2. And then we plug in our values. Now remember, we're at H2. We have a different pressure now. We're at a pressure of 1 bar. So we're going to use the 1 bar to find these values here. If we go to the table, 1 bar is right here. Come over here. HF is 28.18, and then Hg is 1398.14. But remember, this middle one is the difference between these two. So this one's 1370.23, so we'll use this one in the denominator. Plug in those numbers in. H2 is still this estimate of 297.76 kilojoules per kilogram. We are going to subtract that 28.18 kilojoules per kilogram and then divide by 1370.23 kilojoules per kilogram. Notice the units all cancel, just like they should, because quality has no units. Now just do the math and you get that x2 is 0.1967. Okay, so now we have that. Now if we want to put that over here, we're down 1 bar, okay, so that's our new pressure. So let's draw this line. This is for 1 bar. If we look up the saturation temperature for 1 bar, we have this value right here, negative 33.6. So notice with those, the ammonia, your temperatures get a lot colder than they did with some of the other substances. So here we're going to have negative 33.6. This is in Celsius. So essentially we went from state 1 down to, say, right there. And we know we're on this line because we have this quality. Remember, if we have a value of x that's between 0 and 1, we've got to be right here on this horizontal line where we have the liquid vapor mixture. So we have about 20% of vapor at this point. Okay, so that's how you do that, and hopefully you like that example, and I will see y'all in the next video. Have a great night.